Hi everyone, my name is Laura Treese and I am one of the AP chemistry teachers here at Heritage High School. Today we're going to be going through compound stoichiometry. So for this video, you guys definitely need a periodic table. So this is the AP Resources periodic table. It's posted on Canvas. Go download it and print this. I would highly recommend doing that because we'll be using it all year and you just want to get familiar with where everything is on this periodic table. And the numbers are slightly different than the periodic table we used last year. The other thing you're going to need is a calculator. If you don't have a graphing calculator, I highly recommend that you guys get one. This is what you'll use on the AP exam, and so you just want to practice with what you're using for the exam. You just can't swing a graphing calculator right now. Scientific is fine. I will say I've had my graphing calculator since high school. It's probably 15 years old at this point, and it still works perfectly fine. So if you're worried about investing too soon, don't be. You can't break them. Anyways, we're going to go ahead and get started on compound stoichiometry. Okay, guys, so we're going to get started today with just going through basics of the two main conversions that we use in regards to in compound stoichiometry. So the first thing we're going to talk about is the mole. All right, and if you guys remember from last year, basically a mole is an SI unit. So SI is the international system. It's a system that's used across the whole world for chemistry and science in general, but it's the SI unit for amount of substance. It's just how we measure substances. And it contains 6.022 times 10 to the 23rd particles, sometimes called a chemist's dozen. So in the same way like a dozen is 12, a mole is 6.022 times 10 to the 23rd. And then it kind of goes into a little bit of where that definition came from. So the mole was actually discovered or kind of coined by Amedeo Avogadro. So he was a scientist, and he said that the value of a mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. So what that means is if I have 12 grams of carbon that weighs 12 grams, then I have 1 mole of carbon atoms, and then in that 1 mole, there's 6.022 times 10 to the 23rd particles. All right, so this is a really convenient conversion for us. Basically, it just makes our numbers easier to work with. So that's why we use moles, because you can't go back into lab and say, and I can't tell you to measure out 100 particles of water. We can't do that. And so we use moles to be able to figure out how many particles we were working with from our lab. So our conversion here is that 6.022 times 10 to the 23rd particles is equal to 1 mole of particles. All right, and guys, that can really, it doesn't have to be a sciencey word. That a mole can be anything technically. So I could say 1 mole of basketballs. That means I have 6.022 times 10 to the 23rd basketballs, which is a lot of basketballs. Clearly, we don't need that many. But it can be used for a lot of different things. But the main words you're going to see in chemistry are definitely going to be either particles, ions, atoms, molecules, and formula units. Those are the main units we use in chemistry. So particles really just refers to pretty much anything. Ions is talking about something with a charge. Atoms is really specific elements. Molecules is covalent compounds, and formula units would be ionic compounds. All right, so that's our first conversion, is that 1 mole is equal to 6.022 times 10 to the 23rd particles. All right, the next conversion we use is the molar mass. And the molar mass is the mass of 1 mole of atoms. And to figure out what our molar mass is, we are going to add up all the atomic masses from the periodic table. Now guys, that's something that's kind of important to note, is the difference between molar mass and atomic mass. Okay, so an element's molar mass is in grams per mole, and it's actually equal to the element's atomic mass in AMU. So what that means is basically kind of what the difference is then. I'm going to explain it in terms of oxygen. So let's say, so for oxygen, which is O2, all right, so for oxygen, O2, if I have 1 mole of oxygen atoms, that is going to weigh 30, oops, moving the video, 32 grams. Okay? Now then, that would be my molar mass, because 1 mole is 32 grams. But if I have one atom of oxygen, so one single oxygen molecule, that is going to weigh 32 AMU, atomic mass units. So the AMU refers to the mass of like the atom, one singular atom, whereas the molar mass is the mass of a mole. And they are numerically the same number, but they're vastly different scales because obviously atoms weigh nothing, basically. Um, so, yeah. And then molar mass would be our other conversion factor. So, yeah, we can use that to get from grams into moles. Then it kind of has the example down there of molar mass. Then over to the left, over here, we have a mole map. This is helpful if you are struggling with conversions and kind of confused on like, I don't know where those conversions are coming from or how to get to them. That can be kind of a helpful place for you to look. All right. Now, guys, I'm going to tell you guys two of my catchphrases here that are very important for AP and just chemistry in general. So my first one is really specific to like chemistry in general. And I always say, when in doubt, oops, can't spell. When in doubt, moles it out. And basically what I'm saying by that is if you don't know what to do, always, always, always get to moles. So convert to moles because we can do a lot more once we're in moles. So when in doubt, moles it out. And then step 2 is going to be, or my second kind of phrase that you're going to hear me say a lot is for AP chemistry specifically, if you think it, write it. And this is really important for our FRQs. So you can't just skip steps. Don't just magically convert something. Um, Make sure if you think something and you're thinking about doing something that you're writing it down. Okay? All right. So we're going to start with our first problem here. And I'm going to tell you guys this one is probably one of the harder problems that we are going to do today. So I'm starting it off really complicated and then actually we'll do some easier problems as we go. I don't know why I did that, but I did. All right. So this says number of hydrogen atoms in 9 grams of water. All right. First thing I always like to do with a problem is I always need to figure out where am I going and what am I starting with. All right. So what am I looking for in this problem? It says number of hydrogen atoms. So that's my where am I going? That's my end goal is to get to hydrogen atoms. And then where am I starting? I'm starting with 9 grams of water. Okay, so I'm going to draw my train track. I'm going to draw a pretty big train track because I know that this problem has multiple steps. All right, and we always start with what's given. So in this case, I was given 9.0 grams of water. Water is H2O. All right, I'm going to ask myself the question, is grams of water what I'm looking for? Is that my end goal? No. So if no, drop it low. So we don't want grams of water, so we're going to drop our units, grams of water, low. Okay, so now you're like, okay, well, what do I do now? All right, remember my phrase, when in doubt, moles it out. So we want to get to moles. So anytime we have grams, in order to get to moles, we have to use our molar mass. All right, so look at your periodic table, add up all of the masses, the mass of hydrogen times 2 plus the mass of oxygen to get your molar mass of water. And I got that my molar mass is 18.016 grams of water. All right, and my molar mass is always equal to 1 mole. That's 1 mole of water. Okay, guys, now moles of water, is that what I want? No. So if no, once again, we're going to drop it low. All right. I want atoms of hydrogen. So as you can see, we are currently in units. Our units are currently water, moles of water. But I want to be in just pure hydrogen. So since I have different substances here, I have to use what we call a mole-to-mole ratio. And in this case, it's our mole-to-mole ratio inside of our compound. So basically, what I want to look at here is how many hydrogens are in each water molecule. So I want to convert from those water molecules into those from those water into hydrogen. So for every one water that we have, it's made up of 2 hydrogen. So 1 mole of water contains 2 moles of hydrogen. The reason it does is because of our formula. Since our formula is H2O, if I have 1 water, it has to have 2 hydrogens. Keep moving that camera. Sorry, guys. It has to have 2 hydrogens. So for every 1 mole of water, it's 2 moles of hydrogen. All right. So now we're back. Is moles of hydrogen what we want? No. So if no, we drop it low. All right. We want to be in atoms. So for every 1 mole of hydrogen, it is 6.02 times 10 to the 23rd atoms of hydrogen. Is atoms of hydrogen what we want? Yes. Yes, it is. So now we can go ahead and solve. All right, and so to solve, we need to multiply across the top and then divide by the product of the bottom. All right, so go ahead and plug that into your calculator right now. You can pause the video if I go a little too fast with the solving part. Put that into your calculator. Okay. So now, guys, sig figs are super important in chemistry. In fact, a lot of times in AP, if you don't have sig figs, they will not count your problem. So make sure you always include your sig figs. Since this is dimensional analysis and everything in my train track, except for my given, was just a definition value, then I'm going to go with my given for sig figs. So my given has 2 sig figs. So my answer needs to have 2 sig figs. So my answer is 6.0 times 10 to the 23rd atoms of hydrogen. And I always circle my answer so it's easy to see. Okay, so we went kind of slow for that problem, so I'm going to speed it up for the rest that we're going to do together. That way, if you need to rewatch this, you definitely can, but hopefully you guys kind of already know this. So our next problem says how many grams of propane contain 6.02 times 10 to the 21 molecules. Okay, so take our given, 6.02 times 10 to the 21st molecules of propane. All right, is molecules what I want? No, it's not. So if no, drop it low. And when in doubt, we are going to moles it out. So we want to get to moles here. So I know that there are 6.02 times 10 to the 23rd molecules in 1 mole. All right. But moles is not what I want. I want grams. So I'm going to, once again, drop it low. And in order to get to grams, I'm going to use my molar mass. So for 1 mole of propane, it's equal to my molar mass. So add up all your masses from your periodic table. Take a second to do that. Again, you always are welcome to pause it if I put the number too quickly for you. But I got 44.094 grams of propane. Grams of propane is what we want, so now we can solve. So once again, multiply across the top and then divide by the product of the bottom. All right. My given has 3 sig figs, so my answer should have 3 sig figs. So I got 0.441 grams of C3H8. Boom. Okay. Next problem says how many moles are there in 100 grams of nitrogen gas? Okay, guys, so one thing about nitrogen you may have forgotten is it's one of 7 special elements. So these 7 elements, when they're by themselves, always come in partners. I always remember it by Winkelhoff. Personally, I know Mr. Oglesby likes "I have no bright or clever friends," that sentence, but I like Winkelhoff the word. So those are the 7 diatomic elements. So when they're by themselves, they always come in their gas phase. Okay, so that's just important to remember. So it's not just in, it is into, which is important to remember. Okay, so once again, we're going to take what's given. So I have 100 grams of nitrogen. Grams is not what I want, so if no, drop it low. All right, and when in doubt, moles it out. So I want to get to moles. So I'm going to take my molar mass of nitrogen, which is 28.01, and I know that my molar mass is always equal to 1 mole. So that's 1 mole of nitrogen. Moles is what I want, so I am done with this. So now I can multiply across the top, divide by the bottom. My answer, or my, oh my goodness, I'm sorry guys. My given has 3 sig figs, so my answer should also have 3 sig figs. So I got 3.57 moles of nitrogen. Great. All right, 3 more. I'm gonna do 3 more together and then practice for you guys after that. Okay, so this next one says, how many moles of carbon dioxide are present in 4.55 times 10 to the 24th molecules of CO2? So I'm starting with moles, and I want to, or I'm starting with molecules, and I want to end in moles. All right, so once again, always take what's given. So that is 4.55 times 10 to the 24th molecules of CO2. Molecules is not what we want, so if no, drop it low. And when in doubt, moles it out. So we're going to get to moles. So I know that there are 6.02 times 10 to the 23rd molecules for every 1 mole. So then I can solve for it. So multiply across the top. Sorry, moles of CO2 is what I want. So I'm going to solve, multiply across the top, and divide by the bottom. Get into your calculator. Our given has 3 significant figures, so our answer should also have 3 significant figures. So our answer is 7.56 moles of CO2. Okay, so those were all review and probably not new concepts for most of you, hopefully. The next 2 might be new concepts for some of you. They might not for others. I don't know. But I'm going to show you guys. These are 2 kinds of conversions that we'll use much more later in the school year. But we just want to go ahead and introduce them now. So if you're kind of like, oh, I kind of get what you did, but I don't fully understand, it's all good. We're going to use it more later in the year. We just wanted to start getting you guys familiar with them. As long as you know the first 4, how to do the first 4 problems that we just did, you should be great for this unit. But just want to kind of start getting these in your head and working a few of these problems so that you guys are prepared for later in the year when we use these more often. So in this first one, I'm going to show you guys how molarity can be used as a conversion factor. Okay, so it says how many grams of sodium hydroxide must be used to make 500 milliliters of a 2.5 molar sodium hydroxide solution. Okay, so if you guys remember, molarity, and I'm going to write up here, molarity is equal to moles divided by liters, basically. So instead of having this like 2.5 molar solution, really, this could say that, I could say that, my molarity is equal to 2.5 moles per 1 liter. And then I can use that as a conversion in my problem. Yeah? Okay, so let's see how we would do that. All right, so first things first, take what's given. So our given here is 500 milliliters. Guys, I knew that that was my given because I know that molarity is never going to be a given. Just so y'all know, kind of for you as well. If you're given a molarity, it's never going to be a given in a stoichiometry problem. All right, my volume is in milliliters. My molarity is in liters. So that means I need to get to liters. So I don't want milliliters, so I'm going to drop it low. All right, and I'm going to use those metric conversions. I've made a few videos, or I'm in the process of making a few videos right now that are going over concepts from pre-AP that we're not really covering in class, but are being used. So if you're kind of like, I don't know metric conversions, maybe go check out that video. There's also one on sig figs if you're struggling with that too. So I know that for every 1,000 milliliters, it is 1 liter. Okay? Now then, liters is not what I want, so I'm going to drop it low. And this is where I'm going to use that molarity. So for every 1 liter, it contains 2.5 moles of sodium hydroxide. But moles is still not what I want. I want grams. So one more time, I'm going to drop it low. And then for every 1 mole of NaOH, I know that it weighs 39.998 grams. So using my molar mass there. All right, grams of NaOH is what I wanted in this problem. So now I can solve. Multiply across the top, divide by the bottom. Answer should have 3 sig figs. So I got 50.0 grams of NaOH. Okay, guys, last problem. And again, just like number 5, this one is something that some of you may already know, some of you may not, but it's a conversion that we use more later in the year. All right, so this problem says how many liters of oxygen gas are there in 3.46 moles at STP? And guys, that STP is really important, and that's how we know we can use this conversion. So our last unit of the year last year was gases. And for gases, we learned that at STP, rewrite that, at STP, all gases have the same volume. So that means that 1 mole of any gas at STP is equal to 22.4 liters. Now, we can only use that conversion when we see that magic STP. And STP stands for standard temperature and pressure. Okay, so that means this conversion becomes really easy because I know that 1 mole is always going to be 22.4 liters because it's at STP. All right, so once again, we take what's given. So that is 3.46 moles of oxygen. Moles is not what I want, so if no, we're going to drop it low. And I know that 1 mole of oxygen is 22.4 liters of oxygen. Okay, liters is what I want, so multiply across the top, divide by the bottom, and 3 sig figs, so I got 77.5 liters of oxygen. Okay, so the next 4 problems or the next 8 problems on there are all more compound stoichiometry problems. You guys can use those to practice now. I will post the key for you on Canvas so you can check them out to make sure you're doing it right. If you have any questions, feel free to email me and I will be happy to help you. Or if you're like, I never really got this last year, feel free to email and we can set up tutorial times to help get you guys on track. All right, have a good day.